Hello everyone, in this video I'm going to show you how to solve MOSFET examples under the small signal model. So before I start, I'm going to tell you the different configurations that might happen that you might see in any examples of the MOSFET, small signal analysis. You might have a common source or a common gate or a common drain. Okay? If you have a common source, then the gate and the drain, one of them is going to be the input and one of them is the output. Similarly, if you have a common gate, then the drain and the source, one of them is the input and the other is the output. And the drain, one of the gate and the source is the input and the other is the output. But the question is, which one is it? Can we choose any one of them to be the input or any one of them to be the output? Actually, you do not. Most likely, when you get an example, what you'll see is that you will have the input and the output is like that. So if it's a common source, the input is the gate and the output is the drain. Okay? If it's a common gate, then the output is the drain and the input is the source. If it's a common drain, then the input is the gate and the output is the source. And that's an easy way to remember these configurations. Okay? So the one thing that you need to take care of and make a notice of is that when we have a common source, that gain and the drain, the gate is the input and the drain is the output. When we have a common drain, then the gate is the input and the source is the output, which means that the gate cannot be an output. The gate is always an input. Similarly, the drain cannot be an input. It's always an output. Okay? The drain cannot be an input. Okay? The source, sometimes it's an input and sometimes it's an output depending on the configuration, whether it's a common gate or a common source. Okay, so you always memorize, put this triangle, okay, and what I call the GSD triangle, okay, and always keep in mind that the gate is always input and the drain is always output. Okay, so to our example. Let's solve this example and find out how we could solve, because it's basically, this example is going to capture a lot of the ideas that you might see in any MOSFET transistor example. Okay? In this example, it says that the MOSFET transistor is biased through this configuration. RG is biasing the gate to keep it at a biasing level. The drain is connected to a resistor and then to a voltage supply called VDD of 15 volts. It's a common gate, it's a common source, and which means that the input is fed to the gate and the output comes out of the drain. So you might be asking, why do we have these capacitors? These capacitors are assumed to be large, and the role is to bypass the DC, is to block the DC from, is to block basically the DC. So they act as a short circuit in case of AC, and they act as an open circuit in case of DC. So basically they couple the input, they're called basically coupling capacitors. What they do is that if you have a DC supply from here, only the AC is going to pass. So if you have an input of the input biased by some value, this transistor is not going to see except this change in the voltage, because we do not want to mess up with the voltage, the DC voltage of this gate, because we already have configured this DC voltage of the gate through these transistors. Okay. So, let's solve. What do we have? We have a threshold voltage of 1.5 volt, Kn is by this value, and the early voltage, which is 1 over lambda, is 15 volts. Okay? And the required is to find the voltage gain, which is V output over V input, okay? AV, V output over V input, Rin, which is the input resistance seen by the input source, okay? And the maximum V input value that could act, that could let this transistor, that could let this configuration act as an amplifier. Okay? So whenever you have all of these requirements and you're required to find the value of the AV voltage, the voltage gain basically, which is AV, then you need to solve the problem on two steps. The first one is the DC, to get the operating point, okay? And I'll talk later about what an operating point is. And then you solve the AC. And then from the AC circuit, you will be able to write down the values to find the values of AV, RN, and VN. Okay? So let's first solve the DC analysis. Okay? The DC analysis, you let the capacitors as open circuit, and you neglect any AC signal. If you have any AC source, you neglect it. You short circuit it basically. Okay? So let's draw the circuit. That is VDD, 15 volts, RD, and then a gate connected to a gate resistor connected to the gate or the transistor, and then to the ground. I do not have to worry about this capacitor, and I do not have to worry about the load. Why? Because it is an open circuit. I do not have to worry about this as well, because it is an open circuit. Whatever comes after that, I do not care about that. Okay? So this is what the DC sources are seeing. This is the circuit that the DC source is seeing. Okay? So, what do we want to calculate? The main thing that we want to calculate from this DC circuit is to calculate the operating point. And what do I mean by operating point? If you look at the aim of the problem is to find the value of the gain. Okay? And the value of the gain comes from the DC equivalent model. And if you remember that the DC equivalent model is, as we will see in a moment, is affected by GM, the transconductance. Okay? In order for you to calculate, that's VGS, that's the gate, that's the drain. Okay? In order for you to calculate, that is roughly speaking, that's the input, V input from the ground, and that is our load, and this the V output. Okay? Roughly speaking, this will be the circuit. I'm going to draw this in details. However, what I want to point out to you is to give you the big picture. The big picture is that we want to calculate the AC small signal, because that's basically, by the end of the day, that's what we need. This is what we are shooting for. The transistor is going to amplify the input signal to the output signal. So it's going to give me an output signal, which is an amplification of the input AC signal. The input AC signal is very small, and the output signal, I want an output signal to be very large, and that's why I pass it to a transistor. And that's why I need to work on an AC equivalent circuit. And it turns out that the AC equivalent circuit is affected by something called the GM, the transconductance of the transistor. Okay? And this transconductance is affected by the DC analysis. If you change this voltage, then you expect a different response from the circuit. You might not see the amplifier amplifying that much, or perhaps if you increase the voltage, you might see it amplifying a lot. How is that? That comes into the picture through the value of GM. So the configuration of the DC affects the value of GM, and thus affects the whole gain. So that's why we want to calculate the operating point, which is, in other words, we want to calculate the value of GM. Okay? Mainly it's the GM, however, there might be some other stuff as well, as we are going to see. But it's mainly, in all of the problems, you need to calculate the value of GM. What is the value of GM? GM equals twice ID over V over drive, which is twice ID over V GS minus V threshold. Okay, so I need to calculate the value of ID. What is the drain current? Okay, which is that value. Okay, Of course, the drain current is supposed to be this value, but I'm sure that this drain current is the same as that one because there is no current passing to the gate. Okay, this is a capacitor, and by capacitor here I mean that the gate is connected to a capacitor. Why? Because it's a metal oxide semiconductor field effect transistor. Metal oxide. So metal, then a layer of oxide, which means that it is a capacitor. So there is nothing really, there is no current flowing to the gate. Okay? So the value of ID is the same as this value. Okay? So I need to calculate the value of ID through this configuration, and I need to calculate the value of VG, and then subtract it from VS. VGS is VG minus VS, and then subtract it from the V threshold to calculate the value of GM. So let's find what ID is. ID equals, of course you can fairly assume that the transistor is operating in a saturation. Whenever we are operating the transistor as an amplifier, then it's operating in the saturation regime. Why? Because the transistor operates acts as an amplifier when it is in the saturation regime. You cannot draw this small signal, AC analysis signal, the small signal model, you cannot draw it unless the transistor is acting in a saturation regime. You might say, yeah, okay, how do I guarantee that this configuration will yield a transistor acting in a saturation regime? Because this drain is connected to this gate. Okay, so the drain is connected to the gate. Of course, they have the same voltage value. Why is that? Because there is no voltage drop over the resistor, no current, so there is no voltage drop, which means that the gate is equal to VG, okay, equals VD, which means that VGS equals VDS, which means that VGS minus VT is smaller than VDS, which is the condition of saturation. Again, VGS minus the threshold voltage is less than VDS. Why did I just subtracted a value, a positive value from the left-hand side, and then I get the this inequality, which is the condition for saturation. So let's put the equation for saturation, half Kn multiplied by V over VGS minus VT all squared. I know VT, I know Kn, but I do not know VGS. Okay? I do not know what the value of VGS is. But also I do not know what the value of ID is. And that's why I cannot calculate this, I cannot calculate anything from this equation. Which means that I need to find another equation in order for me to calculate the value of VGS and the value of ID. Okay, so what is that other equation? If you look here, you'll find that this is VGS. Okay, so that's a positive and that's a negative. Okay, and what I'm going to do is that I'm going to take, of course, this RD equals 10 kilo ohms. Okay, and what I'm going to do is that I'm going to take, let me erase this. I'm going to take RD equals 10 kilo. I'm going to take KVL in this loop. Okay, this is the loop that I'm going to take KVL at. Okay, how do I take KVL? Kirchhoff voltage law. The current passes from the high voltage to the low voltage, and that's why I put above plus and below a minus. Okay, and this is the value of VDS. Okay, and that's VDD. Okay, let's take Kirchhoff voltage law. So Kirchhoff voltage law tells us that the sum of the values of the voltages in a loop, in a closed loop, is 0. Okay, so let's begin from the bottom. The bottom is VDS, so 0. Okay, and I go up, so I have VDS. Okay, with a positive sign. Why? Because it's in the same direction of motion, okay? So I'm moving from down to top. So VDS is from down to top, which means that it has a positive sign. Again, another voltage from down to top, okay, which is plus ID multiplied by RD. Okay, so why did I assume that the voltage has this direction? Because the current has the opposite direction. So we know that the direction of the voltage is from the negative to the positive. And how did I decide that this is the negative and this is the positive? Because the value of the current passes from the high potential to the low potential. So that's why plus is on top and the minus is at the bottom. Okay, and you can assume that this is connected to VDD, which means that plus minus VDD. So that is the value VDD. Okay, so this connection means that there is a voltage source whose positive is connected to this terminal and whose negative is connected to the ground, which means that this is minus VDD. Okay, so that is opposite to the direction of motion. I'm moving from down to top and back down again. So I'm moving in a loop. Okay, that's basically KVL, Kirchhoff voltage law. Okay, moving in a loop. So that's minus VDD. And then since I moved back to the ground, so the voltages equate to 0. Okay, so again, VDS. What is the value of VDS? We know that the value of VDS equals the value of VGS. Why? Because this gate is the same, has the same potential as this drain. So that's VGS plus ID multiplied by 10K. Okay, let's remove this K and put it above. Minus 15 equals 0. Okay. So VGS equals 15 minus 10 ID. Okay? VGS equals 15 minus 10 ID. That's the second equation, and that's the first equation. Two equations and two unknowns. Let's remove VGS and put 15 minus 10 ID. So ID equals half Kn, which is 0.25. VGS equals 15 minus 10 ID minus 1.5 volts. Okay, squared. So this is the value of VGS. Okay, from here. So after solving this quadratic equation, you get two values for the current. One of them 1.72, and the other is 1.059 milliampere. One of them is correct, the other one is wrong. Okay, so you need to find a way to figure out which one is the correct one. And the key is to look at the value of VGS. VGS equals 15 minus 10 times 1.72 if ID1 was correct. And VGS is going to be 15 minus 10 times 1.059 if ID2 was correct. Okay? So if you look at this value, this is negative and this is positive. Okay? This value is equal to 4. Roughly speaking 6, so that's 4.4 volts. Okay? So this value is positive. Okay? The negative value, of course, is the wrong one. Why? Because I do not expect that this value is going to be negative. Where shall the negative come from? We have 15 volts and 0 volts. You do not expect any negative voltage value. VGS. So this is the correct one, and this one is rejected. Okay, so we continue on VGS. So the GM equals, from this value, ID over VGS minus VT, twice 1.059 over 4.4 minus 1.5. So when you do the math, you get the value of GM, which is equal to milliamperes, 47 0.725 milliampere per volt. Okay, so when you do the math, you get the value of GM equals to 0.725 milliampere per volt. Okay, what about the operating point? Yes, so this is the operating point that we're looking for. Do we need to calculate something else? Actually, we do. Why? Because the early voltage, which is lambda, lambda is not given to be 0. The early voltage, VA, early here is the name of the scientist. Okay, early voltage supposed to be infinity. If VA equals infinity, then lambda equal to 0. Okay, but VA is not given to be infinity. It's given to be a finite number, and that's why you need to calculate the value of RDS, the resistance from the drain to the source. Sometimes people calculate the value of GM, calculate the value of GDS. Okay, so they calculate the value of GM and calculate the value of GDS. Okay, I like to calculate the value of RDS, which is the inverse of GDS, for a reason that I'll show you later on. What is the value of RDS? RDS equals VA over ID, which is equal to 50 over 1.059 milliampere per volt. So that is, roughly speaking, 47 kilo ohms. Okay, equals RDS. So these are the two values that you need to calculate. Okay? So, given these two values, let's go to the AC analysis. With the AC analysis, so GM equals 0.725 milliampere per volt, and RDS equals 47 kilo ohms. Now you know what the operating point is. Okay? The AC analysis. AC analysis. Okay? So we need to calculate, we need to draw the AC model. You have the gate, okay, and then you have the drain, and having a current source. And since it's a dependent current source, then I draw it as a rhombus, okay, and then connect it to the source, and then to the drain from the top. And since I have a finite value of early voltage, lambda is not equal to 0, then I do have a resistance in parallel of value RDS between the drain and the source. Okay, so that is the AC model of the transistor. We need right now to connect the drain, we need to connect the gate, and we need to connect the input and the outputs, okay, as well as the R load. Let's begin with the input. The V input is coupled to the gate through a capacitor, which is assumed to be short, and that is why the input source is going to be, okay, so that's the input, okay, and the source is connected to the ground. the drain, we have a resistance of RD equals 10 kilo ohms, okay? And the resistance is connected to the drain from one side and to the VDD from the other side, which is a short circuit to the ground, okay? So that is RD, okay? Okay, so that's mainly what you might see from a perspective of a regular transistor. However, for this specific example, you have, normally we see this example a lot, we see this circuit a lot. So pretty much you're going to draw this circuit all over the examples that you might see as a common gate example, okay? However, for this particular example, we have the gate connected to the drain through a resistor, and that's why we need to connect this to a resistor, okay? And we have an output signal from an output resistor from the drain, and that is the output, okay? And this is the value of GM VGS. VGS. RG. Okay? So, what do we need to do next? We could take all these capacitors, all these resistors in parallel. Okay? Then I'm going to omit these and put them as a single resistor RL dash, which is equal to RDS in parallel with RD in parallel with RL. Okay? And we have the value of the output here. Okay? So, what is required? Required to get AV, which is V output over V input. Let's do the analysis and find what the value of V output is and find it as a function of the input. Okay? So we start with this terminal. You have a current passing through. Of course, we expect that this value is going to be neglected. IG, roughly speaking, equals 0, because this is a 1, how much is it? 10 mega ohms. Okay? Of course, this is an approximation. Okay? If you want to not approximate this value, you could, and in that case, you need to solve you need to analyze the whole circuit using a regular basic circuit theory, and you'll get, roughly speaking, the same results, assuming that you're going to use the value 10 mega ohms. However, for the sake of simplicity, I'm going to assume that the 10 megas are very large to the extent that no current is passing here to the resistor. And that's why the current passing here is called GMVGS as well. Okay? So, the value of the V output equals current is passing from down to top, from the bottom to the top. And that's why it's positive, negative, from the high potential to the low potential. Okay? However, V output is from here to here. Okay? Which means that it's the opposite of the voltage over this resistor. Okay? So it's the negative of the value of the voltage over RL prime. Okay? Which equals GM VGS, that's the value of the current. Okay? I like to call this small v. Okay? GM VGS with a negative value. Okay? That's the current, and multiplied by the resistor, which is RL prime. Okay? So that's Ohm's law. Ohm's law. Current multiplied by the value of the resistor gives us the value of the voltage. So V output equals negative GM. What is VGS? VGS is the gate to the source, okay, which is the same as input because the source is connected to the ground. The negative V input, RL prime. So V output, AV equals V output over V input equals negative GM RL prime, which is equal to, you do the math, you get the value. So you recall that this value is not a positive value, it's a negative value. And this is valid. Why? Because you expect that the transistor usually has a negative sign. When you input here a sine, okay, a sine or a cosine, you get here a negative, the inverted version of this value. Okay, the value is AV equals negative 3.3 volts per volts. Whether you put volts per volts or you do not put it, it doesn't really matter. Okay, now to the R input. What is the AC source seeing? You need also to calculate the value of the source, the value of the R input. Okay, the value of the R input is actually it's calculated without neglecting the RG. Because if you neglect the RG, R input at RG very large, of course it's equal to infinity. Okay, but however, if you want to calculate the actual value that this input source is seeing, you need to calculate R input equals, okay, V input over I input, where I input is the current passing here. Okay? So let's neglect this for now and find what the current is passing here. So the current here, let's do KCL. Okay? So right now, what are we shooting for? We're shooting for R input, which is V input over I input. So you need to find the value of V input as a function of I input and divide them together. Okay? Divide one over the other. What is the value of V input? Let's take KVL in this loop. Okay? V input that is plus minus I input RG what is the value of the current that is passing here? Here it is passing I input minus GM VGS. I input minus GM VGS, which is V input. So I input minus GM VGS, which is the value of V input, okay? Multiplied by the value of the resistor RL prime, okay? And this is equal to 0, okay? Then you do the math, and then you get the value of V input over I input equals to, which is Rn Rg over 1 plus Gm RL prime, okay, which goes to infinity when Rg goes to infinity. When Rg is very large, then you expect that this value will go to infinity. Okay, what is this value? You can substitute by yourself by the values, which is equal to R input is equal to 2.33 mega ohms. Okay, and this is the value of R input. What's the final thing that we need to calculate? We need to find the value of V input, okay, the maximum value of V input, in order for this transistor to operate as an amplifier. And the mathematical meaning of operating as an amplifier is that we need this transistor to remain in the saturation region. We do not want it to move to the linear region. Why? Because this is the region where we want to have the transistor as an amplifier. Okay, so maximum V input is when transistor is a MOSFET is in saturation. Okay? Which means that V ds has to be greater than or equal to V gs minus V over minus V threshold. Okay? So remember that here I've written down the V as a lowercase, this V as a lowercase, this ds as an uppercase. Okay? Which is totally different from what I was doing here. VGS was small, lowercase v, lowercase g, and lowercase s. Okay? And this brings us to a very important concept. When you write down VGS, then this means that it is DC value. When you write down VGS, then it is AC value. When you write down VGS, then it is DC plus AC. Okay? VGS. So uppercase, uppercase, lowercase, lowercase, lowercase and uppercase. Okay? So that's DC plus AC. Which means that here we're dealing with DC plus AC. Okay? The transistor has to be in the saturation region, and you need to calculate this using this equation where VDS is DC plus AC and this is DC plus AC. Okay? What is the value of VDS? That is VDS plus VDS. Has to be greater than or equal VGS plus VGS minus 1.5 volts. Of course, in the DC, this VGS equals that VDS. Okay, and the S's are equal. Okay, so there's no the source is shorted to the ground, which means that the condition is VD has to be greater than or equal. So that's basically the input. All right, the input minus 1.5 volts. Okay. What is the value of VD? It doesn't really matter whether you put it VDS or not. Okay, so what is this equation telling us? It's telling us that VDS has to be greater than the input voltage minus 1.5 volts. And this VDS is actually the minimum possible value of the drain to source. So it doesn't really matter if I write here minimum. Okay? Which means that the minimum value of the voltage of the drain to source has to be larger than V input minus 1.5. Okay? What is the value of VDS? VDS is actually this drain voltage minus the source voltage in the AC signal. Is that right? That's in the AC signal model. Okay? Which is equal to the output. So you know that VDS min is equal to the value of AV, negative voltage, negative value, okay, multiplied by V in maximum. Okay? Why? Because when V input is very, very high, then you expect that this VDS min, this is the same as if I write down like that. Okay? AV, since AV is negative, okay, then Vn maximum corresponds to VDS minimum. Okay? So I could write it in this way. So I could write down, substitute by this here, then I could get AV, Vin max greater than Vin max minus 1.5. Why? Because I know that the AV is negative, so the maximum voltage corresponds to the minimum voltage DS. Okay? So when you do the math, you find that Vin has to be maximum, has to be smaller than 1.5 over 1 plus 1 minus AV, okay? But since this is negative, then I could take the absolute value and write it in this form. Okay? I could take the absolute value and write it in this form, which is equal to 0.35 volts. Okay? So that is the maximum value of input signal from the input source that could oscillate. That is possible. Okay, so this is the input maximum. Okay? And for the V input minimum, you expect that it's going to, it doesn't really matter for to keep you cannot obtain it by looking at the saturation region. Okay? So for the V input maximum, we wanted to find the V input maximum that corresponds to keeping the transistor in the saturation region. However, for V input minimum, it is the one that is found by finding the VD that keeps the current here a positive value, which means that it should not exceed VDD. So if you want to find the V input minimum, VDS has to be less than VDD. Okay? So hopefully this example has covered a lot of the questions that you might face in any common source example. And what did we cover? We covered finding the voltage gain, finding the input resistance, and finding the maximum input voltage. And we have seen that this, in order to solve this problem, you need to first calculate the DC analysis, to do the DC analysis, then the AC analysis, and then finally you need to solve for the AC and DC together if you were to find the maximum input voltage. Okay? If you have any questions, please let me know.